Well, a warm welcome to everyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a little more function work, transformations, and such. We're going to get a glimpse of some parent functions today. That's right. And we're focusing on graphs. So we're taking a look at the graphs of some functions, starting with this sort of pieced together function. There's not an equation that defines function, it's just a bunch of pieces. We can verify that it is a function because it passes the vertical line test, right? Any vertical lines drawn will cross through at most one point. And to be clear, this here is an open circle. So this spot I'll make a little bit clearer. It's a closed dot. Okay, and there are some common questions that you're going to have to be able to answer if you want to truly say that you're competent, if you want to be competent in working with functions. This is going to help you not only for Algebra 2 or intermediate algebra, it's going to help you for pre-calculus, and it's definitely going to help you once you're analyzing things in calculus and beyond. So let's take a look at this. Reminders that with a function, the input of a function, which goes right here, these are x values. And this one has the input of an input. Whenever we're evaluating functions, we're basically finding the y value, the output. So let's get started. Oh, of course. Let me say, give yourself about 5 or so minutes to work on this, and then let me show you some of the other problems that I have on this assignment. You can pause the video when you want to, take a close glance, given the graphs below, identify the parent function and the transformations, write the equation of the transformed function. So I'm going to go through these so that you can either pause the video, take a mental image, plot some important points that you might notice. I'll go through all of these functions. I do have some dots emphasized, like a dot here at 3, 2. And there's another dot somewhere around here at 8, 5. Somewhere around there, let's say. The third function, here we go. So you need to know the parent function. I almost said the parent function, whoa. And you also need to know the transformations that have been done to it. Then we'll finish off with sketching graphs of our own, using these 3 function equations and grids. So you've seen everything there is to see. You can rewind it if you need to check again. But give yourself about 10 minutes for the graphs, 5 minutes for these, for a total of like 15 minutes or so. Try the problems out for yourself first, and then when you're ready, you can unpause the video, come on back, see how we did it here. Okay, great. So let's get started with these. First, we want to evaluate, which means we want to find the y values. That's essentially what it's asking us to do. And we're going to do that by simply looking at the graph. So f of negative 8 means the x value is negative 8. Let's take a look at the y value. You have to count carefully. Here is negative 8. And how far down is that? I put a nice dot there. 1, 2, 3, 4, 5, 6, 7, 8. Well, all right. That means that the value of the function when x equals negative 8 is also negative 8. That's because the y value is negative 8. Now let's take a look at f of 4. F of 4 is where there's a cutoff point here, but there's an actual dot located on the left piece. So we're going to use the location where there is a dot as the y value. And if we count 1, 2, 3, 4, hey, look at that. F of 4 is simply 4. Again, because the y value is 4 when we look at the x value of 4. This open circle is not a point. It means the function kind of starts there, but not really starting at 4. It starts immediately after, you might say. Okay, and part C, f of negative 4. So what we have to do first is we have to figure out what is f of negative 4. That way we can plug it into the f function. But in order to do that, we need to use x value of negative 4 and plug it into the f function. So here is negative 4. 1, 2, 3, 4. And the y value seems to be... What is the y value? It's supposed to be a 4. It should be that point kind of up there. It's a little bit low, in my opinion. If you would have put 3, that would be okay. I'd be okay with that. It'd be tougher to answer the next question, but you could answer it if this were 3. So let's kind of make two cases. Let's do, could be f of 3 or could be f of 4. It's ambiguous because I poorly drew the graph. So f of 3 would be the function value here at 3, which is clearly 2. That's the y value. But if we use f of 4, that's going to have a y value of 4, just like we saw in part B. So on one hand, you could say that this is equals to 2, and I think that'd be fine. Just in the future, you'll probably have a better graph drawn than the one that I drew. And if you used f of negative 4 equals 4, then you can plug that in and you will also get 4. All right, now let's move on to the interesting questions that say find the solutions. What does it mean, find the solutions of this? Well, this basically means find the x values. So in this case, they're telling us that the y value equals 4. So it's like find the x values when ... y equals 1. So in order to do that, let's draw a a horizontal line at y equals 1. And you'll see that there are several x values which hit the graph at y equals 1. We want to list some of them. This one's off the grid. We don't really have to worry about that. There's not even an x value for it. But here we have negative 2. Here we have positive 2. And here we have negative 5. So those are solutions to the equation f of x equals 1. We're finding x values. So we have negative 5. That's a solution. Negative 2, that was a solution. And then, I believe, 3. Nope, wrong again. Positive 2. Those are our solutions for when f of x equals 1. In other words, if you plug in these x values to this equation, like f of negative 5 or f of negative 2 or f of 2, it will equal 1. And you can go back and check that, see. If we plug in negative 5, the y value is 1. If we plug in x equals negative 2, the y value is 1. And if we plug in x is positive 2, the y value is 1. So those are solutions. Now, in that sense, let's take a look at the next one, f of x equals negative 2. What are the solutions? So they're telling us that y equals negative 2. Let's go ahead and draw a horizontal line at y equals negative 2. Something like that. Oh, wow. It was going so well. I think I just kind of missed it when I drew this. Let's move this just a little bit. Let's move this up just a little bit. That should be good. So again, you can be frustrated with my poor drawing. That's okay. Now I try to make a little dot here. I don't know, it's very subtle, but I try to make a dot there. Maybe I'll exaggerate it a little bit more so that it's clear. Bam. Oh, and at the end we got a little blip. Sorry, my OCD is kicking in, guys. It's going to be a thing. OCD is just strong with math people sometimes. Okay, so we have several points where the graph is crossing negative 2. I see one there at x equals negative 10. I see one here at x equals negative 6. And I see one again here at x equals 8. Is it 8? Might be 9. It's looking like 9. So our solutions are going to include all of those x values. Negative 10, we have negative 6, and we have 9. those are solutions to the equation, because if we plug in those values, like f of negative 10 or f of negative 6 or f of 9, you'll see that that's when we cross through this value of negative 2. Okay, great. We got to step it up, guys. We got to step it up. We are moving. So given this graph below, what's the parent function? There are several parent functions. And based on the shape, you should quickly be able to tell what kind of parent function this is. So this is obviously y equals x squared, the graph of which is a parabola. But there's some transformations done to it because it's not starting at 0, 0. The normal graph would start something like that at 0, 0 and go upwards. This one also looks like it might be stretched a little more than normal. We'll see. So we notice that this vertex location is 3, negative 4. And that immediately tells us something about the transformations. That means this graph has been shifted to the right by 3, and it's shifted down by 4. To see if it's been stretched vertically, we kind of need to see how quickly it goes up. And this is generally pretty easy to do when you have parent functions, so listen up. There are 2 dots located in symmetric points from the vertex. What you need to do from the vertex, this is very important, from the vertex, you need to measure the quote-unquote slope, like the rise over the run. So this is plus 2, and this is over 1. Whatever the rise is from the vertex in that first rise, this is our vertical stretch factor. So this is vertically stretched by a factor of 2. And the way that we write that in an equation now is going to be f of x equals 2 x minus 3 squared minus 4. So let's break that down a little bit. This here is the vertical stretch factor, the V stretch. You could have a horizontal stretch, you can have a vertical stretch. Now this is what's tricky, because even though they're right by 3, when it comes to transformations, whenever you're doing a transformation in life, we do the opposite of what our x's tell us. That's kind of the funny way to remember that. You do the opposite of what your x's tell you to do, and you have a transformation. So if we're going to the right by 3, we're actually going to put x minus 3. And lastly, we have this vertical shift. Now the vertical shift is very cooperative. If the shift is downwards, we're going to have a negative. And if the shift is upwards, we're going to have a positive. So this captures all of the information about the transformation of the function x squared. Great, let's move on. This next one, this is clearly coming from the parent function of the square root graph. The square root graph would normally start at 0, 0, and it would very flatly increase. It would increase, but it would be very flat. In fact, it would get flatter and flatter as it goes. And you can see that for yourself by plotting points, right? The square root of 1 is 1, but the next whole number doesn't come until the square root of 4, which is 2. And it does something kind of like that. Clearly this has been moved. It has been shifted, but it's all been stretched. See how it's kind of taller? The purple is kind of taller. So this point is going to be negative 1, negative 4, which we can describe the shifts. So we can say this is a shift to the left by 1, and this is a shift down by 4. But we also want to notice the vertical stretch, because in the parent graph, we see that from the vertex, again, everything's coming from the vertex. Let's get this point a little bit more. There we go. From the vertex, normally the graph shifts up by 1 and over 1. You see that? It goes up 1, over 1. Up 1, over 1. But if we analyze the stretch of this transformed graph, take a look at that behavior. It's much different. It goes up 3 and over 1. So that means that we're going to have a vertical stretch by a factor of 3. So how do we put all this together? We say f of x equals 3 times the square root of x plus 1. Remember, we do the opposite of what our x's tell us to do. So we're not going to minus 1, we're going to plus 1. And then outside we have the ever cooperative vertical shift. Okay, we see some similarity that the stretch factor is really dependent on this sort of initial rise or fall. So let's take a look at the third. This is obviously going to be coming from the parent function y equals absolute value of x, which normally looks like a v. It would normally go upwards because the absolute value cannot be negative. But in this case, it's obviously been flipped over. So what happens when it's been flipped over? We can also see that it has been shifted because our vertex point is at negative 2, comma 1, 2, 3, 4, 5. So let's indicate that with some smaller text. It is a shift left by 2. It is a shift down up by 5. And let's put that somewhere you can see it. Yeah. Okay. Now let's take a look at this reflection. It's clearly flipped downwards. So this means it has been reflected over the x-axis. In other words, the y values are made negative. The positive values become negative values. But there's still a shift, so that's why not everything is below the graph. But how do we capture this in an equation? And is there a vertical stretch factor? Well, let's take a look. Normally, the parent function goes up 1 over 1. Up 1 over 1. That's the slope of 1. If we take a look at our graph here, it goes down 1 over 1. Down 1 over 1. So it seems to not have a vertical stretch. It was simply flipped over. So this is like a minus 1 over 1. So therefore, the number, the vertical stretch factor, if you want to call it that, is a negative 1. And so the function is going to look like this. Negative absolute value of x plus 2, because we do the opposite of what our x's tell us. And then we have the super cooperative vertical shift plus 5. You're going to really like those vertical shifts. They're very cooperative. And now we have 3 functions based on these graphs. All right, let's keep it moving. We've got 3 more functions to go. Now this time they want us to list the transformations and they want us to graph it. So let's first list the transformations. This is going to be shifted to the left by 2, shift up by 5. What else do we have here? We have a vertical compression. It's sort of like a shrink, because we're not multiplying this by a big number, we're actually shrinking it. We're multiplying it by a third. Vertical compression and a reflection over the x-axis, which means flipping it downwards. So here's how we're going to do it. We're going to graph these shifts first to move the vertex in the proper location. So negative 2 and positive 5. That's looking familiar. It's the same spot as our previous function that we just did. But it's going to go downwards. Oh, I should put vertical compression by 1/3, and it's a reflection. So how do we capture the reflection and the vertical shift? We'll basically go down 1 over 3. So there's a dot, and then we go the other direction, over 3. And see how it's very wide. It's not steep at all. It's not steep at all because it's a 1/3 slope. There we have it. Pretty easy. Right, let's take a look at the next one, which uses the square root function again. So we know what its standard looks like, but let's consider the transformations. We have a shift to the right by 3. We have a shift up by 4. All right. We also have a vertical stretch by a factor of 2. So how are we going to capture that? Well, we have to be a little bit. Let's first plot the vertex location. The starting point is going to be 3, 4. And from there, maybe I need some more of these. Instead of going up 1 over 1, I'm going to go up 2 over 1. Somewhere around there. If you want more points, of course, you can always plug in other points. So I plugged in 4 here. The next nice point to plug in would be 7. So let's try to plug in 7. G of 7, right? That's going to be 2 times the square root of 7 minus 3 is 4. Well, the square root of 4 is 2, so this is basically just 2 times 2, 4 plus 4. So that's going to be at 8. So this is very tall indeed. This should actually go much higher. It should go up to about right there. That might be a little bit too high. There we go. Something like that is perfectly fine. Okay, and the last one here, we're using the cube function. And if you're not sure what x cubed normally looks like, it looks something like this. I call it the Superman curve, right? Looks like it's going up to the heavens to the right, and it's got its arm downwards, you know, kind of superhero. You can imagine. You can strike a pose if you need to. But we have some transformations here, and we only have 2 significant transformations on this one. This is a shift up by 1. It's a vertical compression by a half. But it's also reflected over the x-axis. So how do we capture a reflection there? Just to give you a brief idea of what that looks like, when we reflect it, it basically flips. So what's up is down and what's down is up. This would be the x-axis reflection. So let's try to capture that by starting off with the shift for the vertex. It's going to be located at +1. But then we're going to go downwards. We're going to make this kind of a shape. However, we're not going to go down 1 over 1. We're going to go down 1/2 over 1. So here would be our point, and here would be our point. I know it doesn't look like much yet. It's going to go something like this, and something like this. Now, if you want specific points, again, you can plug in some points, get an exact value. Like if we plug in -2, what do we have here? This would be -1/2 times -2 cubed plus 1. -2 cubed is -8, but then if we multiply it by a -1/2, of course, we're going to end up with +4 plus 1, which leaves us at 5. So there should rightfully be a point right around here. I guess I drew that fairly accurately. And then let's try to plug in +2 and see what happens. So if I plug in +2, this will be -1/2 of +2 cubed, which is -1/2 of 8. So that's going to give us -4 plus 1, which is -3. And so our point here, I didn't really make space for it, but it should be somewhere around the -3. Okay, that's all there is to this. So you're going to continue mastering functions, whether it be through algebra, whether it be through graphs, whether it be through using tables and numerical analysis. In order to transform functions, you need to know the basic types of transformations, shifts, stretches, reflections, and then you need to know how to apply them in an equation, but as well on a graph. You'll notice that some cases, with the domain restriction, the domain will change completely if you shift it. Other functions, like x cubed or absolute value, these do not have any domain restrictions. So even if you transform it, the domain is still all real numbers. But something like a square root function changes its domain when you transform it. Okay, I think that's enough blab out of me. I'll see you guys next time.